Good afternoon, everyone. I hope you've had a fantastic week. I've picked out an interesting review problem for us, and this one is investigating a block and pulley system, but instead the rope has a non-zero mass. How many problems do you deal with block and pulleys where you have to consider the mass of the rope? Not very many, if at all. So if you had to, what would you do? Kind of a good question. We'll answer that in this problem. So essentially we have our block and pulley system here, and block A, the red one, has mass MA, or M sub A, however you'd like to recite that. Block B is the blue one and has mass MB, and the rope connecting them has a non-zero mass, M rope. And so if the total length of the rope is L, and the pulley has a very small radius, and we get to ignore the sag in the horizontal part of the rope, then we have to do the following parts. And here's kind of a visual indication of what is happening there, right? Block B falls, it pulls block A with it to the right, and we get this chunk of rope of length D kind of pulled down with it. And so with all this in mind, let's take a look at the three parts that we have to do. Part A says, if there's no friction between block A and the tabletop, find the acceleration of the blocks when that length D of rope hangs vertically between the pulley and block B. As block B falls, will the magnitude of the acceleration of the system change at all? Right? So really, part A wants us to determine, would the system, or the acceleration of the system of blocks, would that be any different than like if we didn't have a rope with mass? Right? How does that change anything once we include a rope with mass? And so that's what the last part of part A is essentially asking. And part B wants us to do the same calculation in part A, except we use these numbers here. We are going to turn friction back on between block A and the tabletop, and they've given us some quantities here to work with. And our job is to find the minimum value of the distance D, such that the blocks will start to move if they're initially just sitting there at rest. And then for part C, we do the same thing that we did in part B, but we just switch up one number, this mass of the rope. And we need to answer the question, will the blocks even move with this new number? So let's start off with the free body diagrams of everything. We can squish them all in one window and kind of save on some time. Let's start on block A here. We know that the weight of block A is going to be pulling down on it, and we'll have the normal force of the table pushing back on block A as well. And that will have the same length vector as the weight, because the block A will not be accelerating in the y direction as it slides across the table. Okay? It'll just be staying at a level surface the entire time. Let's not forget that there's that rope or string or whatever it was that was attached to the block that's pulling it. So there's going to be tension from that attachment pulling on block A, and that will be pulling to the right in the positive x direction. And since block A's net motion is to the right, there will be kinetic friction during that movement, and it has to be in a direction that resists that motion. So it'll be pointing in the opposite direction to the left, and that's our kinetic friction. There are no more forces acting on block A. That's it. There's only 4 of them. So let's jump into block B. This is going to be simpler because block B doesn't have any horizontal motion. It just moves up and down. So we know that there's the weight of block B acting straight down, and then there will be tension from the rope acting on block B as well. And one thing to be very careful of when you draw these free body diagrams for these two blocks, notice that the tension from block A and the tension from block B, they're not the same length. They are not the same magnitude. They can't be. If they were, the blocks would not move. These two tensions have to be different from one another in order for the blocks to actually experience an acceleration. So very important thing to note when drawing these. Anyway, let's move on. Rope of length D. What are the forces acting on that? Well, we have that chunk of rope's weight that pulls directly down. We also have the tension from block B pulling it down as well, and then from the other side of that chunk of rope, we have the tension from block A side pulling from the other direction. So those are all the forces on our free body diagrams. There's only one more thing that we can include, and here's a very helpful reminder, and it's that objects that are physically connected by things like strings or wires or ropes, or it doesn't matter, they all experience the same magnitude of acceleration. So that means we can include the acceleration off to the side of these free body diagrams, and it will look like this. They all have the same magnitude. They're all A, right? But they just point in different directions. Block A accelerates to the right, and block B and the rope of length D accelerate down as they fall. And that's kind of the reasoning behind that. So what about the sum of forces on block A? Remember, we want the acceleration of like the whole system. So we need to do F equals ma on each of these and get some acceleration expressions. So starting with F equals ma at the top, where m is the mass of block A, we have the following expression for the sum of forces in the x direction. The tension points in the positive x direction, and kinetic friction points in the opposite, so that explains the left-hand side here, and we're setting that equal to ma, where A is in a positive direction, so we're good. We don't have to make any adjustments. We can simplify the kinetic frictional force for mu sub kn in the next line, but we can't go any further until we have an expression for what the normal force actually is. And we can get that from the sum of forces in the other direction. Because, as I mentioned earlier, the normal force on block A and the weight of block A, they have equal magnitude. And the block is not shooting up into the air or diving down into the earth, so there's no acceleration in the y direction. Hence, ma is 0 here. Which means we can just take the weight of block A, move it to the other side, and bam. Now we have an expression for what the normal force acting on block A is. It's just block A's weight. So we can plug this in over here on this side, which looks like this. And we can simplify just a half a step further, really, by exchanging weight for mg. But remember, we're doing weight for mg specifically for block A, so we have to label the mass as block A. And that is as far as we can go regarding block A. So let's make a useful underline under this expression, and we'll come back to it later. Next, we'll move on to block B. And, of course, sum of forces is equal to ma at the top, where m is block B. Easy money in the x direction. You got nothing. The block B does not move in the x direction whatsoever, so we can basically ignore it. Sum of forces in the y direction. Different story. We have the tension pointing in the positive direction and weight in the negative, so that explains the left-hand side. And instead of regular F equals ma, well, we have A pointing in a negative direction, negative y. So F is really equal to minus ma, which I can kind of pull the negative out in front here and write that appropriately. I've also taken the weight of block B and I've exchanged it for mg as well. So there's one last thing that I want to do with this expression here, and I don't like negative ma. I want positive ma. So let's multiply both sides by -1, which just rearranges the left-hand side and gives us what we want on the right. And there's our second underline. We'll come back to this one as well. One more sum of forces. This time it's on the rope of length D. And as always, start from the top. X direction is a joke. Nothing happens there. Just ignore it. Let's go on to the Y direction. We've got tension pointing in the positive from A, and then the other two forces, tension and weight, are pointing in the negative. So that's why it's set up here. Instead of regular MA, we have the acceleration pointing in the negative direction, so it has to be minus MA. And we want to get rid of this minus here, so we'll multiply both sides of this expression by -1, which rearranges things for us a little bit. And we can also exchange the weight of the rope at length D for mg of the rope at length D. And this is our last equation that we're going to make a mark for. And the next thing is to use all of these colored equations that we made a mark of to get the acceleration of the system. And I'll show you what I mean in the next slide here. We want to take this equation plus this one plus this one, and I want to add all the stuff on the left-hand side together and all the stuff on the right-hand side together. And while it's a little messy, we can group things together using parentheses and color code it to make it more visually appealing. So if I introduce the colors, we can see that the left-hand side of the red equation came down here, left hand of the blue here, and left hand of the green there, and then all the other MAs went on their own side over here. Now, before we proceed, notice that we have some terms we can eliminate on the left-hand side. It doesn't matter that they're in parentheses. We'll end up getting rid of them and simplifying anyway, so it doesn't matter. We have a positive tension for A in this red, but we have a minus tension for A in the green. So those will cancel out. And we have a positive tension for B in the green here and a negative tension for B in the blue. So those will cancel out as well. One more thing, we have an acceleration term in every single piece over here on the right-hand side. And since that's what we want to solve for, I'm going to also factor out the acceleration on the right-hand side. So next term, or the next line, excuse me, is all the simplified stuff from the left-hand side. We got rid of the tension terms. And then down here, we've just factored out the acceleration. And if I want the acceleration by itself, I'm going to divide both sides of this expression by the sum of all these masses in the parentheses here. And that is, let's also factor out a g on the left-hand side from all these terms. It just makes things look a little bit neater. So once you factor out the g, now we can divide both sides by the masses, excuse me. And that's what this looks like right here. Now, there's a problem. We can't say that we're done yet. We can't answer part A because what is this? Nobody gave us this value in the problem description. They didn't tell us what the mass of the rope is at some arbitrary length d. They told us what the mass of the entire rope is. So our job is to relate the mass of the rope at length d to the mass of the whole thing. And here's a reminder. I'm going to draw the rope as just, a straight line here, and we were told that it has a length of L and a mass of M rope. I'm going to chunk this rope up into equal segments. So I'm going to take M rope and divide it by L, and here's what we're going to do with it. The mass of the rope at length D is equal to us taking the entire mass of the rope and dividing it by the length, which gives us the mass of an individual tiny unit chunk right there that I've colored in pink. And we want to take this quantity, this mass per length, and we want to multiply it by the length d. And that will tell us how much mass is contained in that chunk of rope. And here was our previous equation for the acceleration. And the term that we want to get rid of is this mass of rope d. So let's take everything that we wrote here on the right-hand side and plug that in for the mass of the rope at length d, which looks like this. Now we can get to answering part A, finally. So the first thing we should do is figure out what's the acceleration of the system before the block even drops and anything happens. So that would mean d is equal to 0, and in part A there's no kinetic friction. So that's also 0. Our acceleration term is going to look like this. Remember, if the kinetic friction is 0, the first term is going to be 0 in there. And since there's no rope that's fallen, well, the last term is going to be 0 as well. So it's really just the mass of block B divided by the sum of all the masses times G. It's a different story when the rope begins to fall, though. And we can figure out what the end result would be if we just take the limit of the acceleration of expression as d becomes L. What does that mean? Well, what is the limit of the acceleration expression as the length of rope that falls becomes the entire length of the rope? Well, if you are familiar with the process of limits from maybe like a pre-calculus or a calculus course, this one is really simple. We're just going to replace d with L, which is nice because now the L's cancel out. We have an L in the numerator and an L in the denominator. So we're left with the following, which looks really similar to the last expression we had before the rope even fell, except now we have the mass of the rope in the numerator. So what's the answer to part A? Well, the acceleration increases when the rope begins to fall, because by the time the entire rope falls down, you get this term. You get a bigger numerator than this term when the rope hasn't fallen. And so that is the answer to part A. And a good question to ask at this point is, how can we be sure that this left term is bigger than the one on the right? Maybe when you take a look at that, you aren't completely sure. Maybe it isn't completely obvious. So let me just take a quick minute or two and show you algebraically why that is the case and how we know that the left one actually is bigger. So I won't even write an inequality between these two terms. I'll just leave it as a question mark, and we will determine the answer at the end once we've done the algebra. So speaking of algebra, the first step is to get rid of g on both sides. We'll divide g out, which looks like this. Since there's nothing on the outside of the parentheses anymore, there's no reason to keep them. So here's our next step. And since the denominator is the same on both sides, we could multiply both sides by that denominator and just eliminate it entirely. And here we have the mass of block B plus the mass of the entire rope is what compared to the mass of block B by itself? Well, the mass of the rope is a positive number. So if you're taking a positive number and adding another positive number, it has to be bigger than what you started with. It has to be, right? And so every single step along the way, the left side has always been bigger than the right. And that's how we came to that conclusion. What about part B? We have this for our acceleration expression, and we were told that we want the blocks to just start, to just barely begin to move. And what would that mean? Well, the acceleration would have to be greater than 0 for that to happen. And if the blocks are not moving, and then they just start to move, well, we can't use kinetic friction. This is a problem. We need to switch. We need to use static friction instead. And so the goal of part B is to use this expression to solve for what D would be. Let's do that next. We're going to multiply both sides by this denominator here. to eliminate it, which gives us the following. I'm going to move this static frictional term with block A over to the other side, which makes it positive. And then I'm going to move the mass of block B to the other side, oops, pardon me, which makes it negative and looks like this. Finally, if I want to get D by itself, I will multiply both sides by L and then divide by the mass of the rope. And that's what this looks like in the next line here. So if we move on to the solution part, now that we have the proper expression, we can plug in the numbers that we were given. And what does that tell us? Well, that says that in order for the blocks to start moving, you need to have a length of rope greater than 0.625 meters to fall down. Well, there's one problem here. We need to answer this to the proper number of significant figures. We can't use 3, and here's a reminder why. We had a single quantity with only 2 significant figures hidden in part C. And remember, we have to report our answer to the smallest number of significant figures in the problem description, no matter what part they're hanging out in. So instead of 0.625, it's really 0.63. And so that is the answer to part B. We need to have a length of rope greater than 0.63 meters to fall in order for the blocks to start moving. Finally, part C. Let's go back to our expression that we just had in part B, and we're going to change the mass of the rope to be a much smaller value. It's that 0.040 kilogram number now. So what happens when we do this? Remember, when the mass of the rope was much bigger, we only needed 0.63 meters of it to fall to get the blocks to move. But if you make the mass of the rope much smaller, this is a problem. This is the answer, but it's a problem. Here's a reminder. The length of the rope is only 1 meter. How are we supposed to get 2.5 times the length of the rope to fall when there's only 1 meter of rope available? So this is an example of a non-physically possible situation. Okay, we can't have this. Just because you get a mathematical answer here does not mean it represents reality. So just a very interesting quirk if you mess with the value of the mass of the rope in your expression. And so if we bring all of our answers together on a single solution card here at the end, here's what we covered. In part A, we said that we said that the acceleration of the blocks will increase because this term on the left, which represents the acceleration of the blocks, this will be bigger after the mass of the rope falls as compared to when it doesn't. We found that the length of the rope in order to get the blocks to move was 0.63 meters. When we answered that to 2 significant figures. And then for part C, we found that no, the blocks will not move for any value of D between 0 and the length of the rope, because in order for the blocks to move, we need to have D longer than the length of the rope for that to occur. So here's all our answers, and I hope that this has helped. Thanks for watching.